Okay.
And you got one person to come in.
But today we start using the Ely, talking about cosmic thought.
Thank you. I want to thank the organizers for inviting me to give this talk. And I'll start with an apology. I was asked to give an overview of 21 centimeter intensity mapping and its outlook for cosmology, but that's not all I'm going to do. Okay, so some teasers. Before that, I'll say that this work is mostly done by these people. Sarah Libanore, a postdoc in my group, applying for jobs this fall, so make sure to look out for that. Chovav, a PhD student, Jordan, a former PhD student, now a postdoc in Pisa, and other people as well, including Julian and Kim at UT Austin. So 2 teasers before I start. One is that, and this is the reason I didn't want to give the standard 21 centimeter talk, because it's always talking about the far future, and people have been promising to measure this signal for more than 20 years now, and we haven't measured it yet. So instead of being gloomy, I thought I'd show you that, I thought I'd focus on cosmic dawn in general and show you that already with measurements from cosmic dawn, we can actually start placing constraints on cosmological models. In particular, we've already been counting thousands of galaxies at cosmic dawn with Hubble and now with JWST, and you can place some of the tightest constraints on some various models of dark matter that have small-scale phenomenology. Okay, so wait about 15 minutes, and I'll show you some of the tightest constraints you can get from these measurements. Another teaser. And this is focused more on the astrophysics implementations of measuring of observations from this epoch, is answering this question. Can we time the onset of reionization? So here I'm really focusing on the onset of reionization, on the beginning of reionization. As people have discussed, Noah gave a very nice talk yesterday about the optical depth tau to the CMB. So as you know, tau, or the CMB, is an integrated constraint on the total duration of reionization. We also have direct measurements of the end of reionization, sensitive to the end of it, from the Lyman alpha forest, from the Gunn-Peterson trough, from quasar spectra, and from 21 centimeter itself, because the signal, the cosmological signal from the IGM should vanish once reionization is over. However, there is no method, there is nothing you can point to that is detectable, that is sensitive to the very first moments of reionization, when the neutral fraction was, the ionized fraction was about 1 to 10%. Okay? So wait 30 minutes and I'll show you something that you can observe and you can detect this the beginning of reionization. All right, so before I do that, I'll do what I promised to do, which is to give a short review and outlook of line intensity mapping in general. So let's start with that. Okay, so an introduction to line intensity mapping. What is the goal? The goal is to go beyond the observables that have served us so well in the past 20 plus years. CMB, galaxy survey, so CMB at high redshift, very clean signal, galaxy survey at low redshift, just counting galaxies as far as we can go. But as we count galaxies, counting them at higher and higher redshift becomes harder because they're faint. The light is too faint to be able to count a lot of them. So the question is really, how do we access this huge volume? Okay, more than 50% of the observable universe is cannot be directly probed by the CMB. Of course, with secondaries you can do that, or with galaxy surveys. So here comes line intensity mapping. And what is the earliest signal? The earliest signal comes from the interaction of CMB photons, or the passage of CMB photons through neutral hydrogen clouds, and the interaction that they have with them. And there are 3 distinct epochs from which you can measure a signal. One is the Dark Ages. This is before any astrophysics is relevant. There are no stars. It's just the fact that the gas cools adiabatically and falls faster. The temperature falls faster than that of the CMB that allows for absorption of CMB photons in the neutral hydrogen clouds. Then there's the epoch of reionization that I just talked about, where the gas is already heated up above the CMB, and we have a signal in emission against the CMB. And in between, there's this cosmic dawn epoch, which will be the focus of this talk. And here there's another onset of the signal of the 21 centimeter, which comes from the fact that the first stars that form shine Lyman alpha photons, and these couple the spin temperature, the excitation temperature of the gas to the excitation temperature of the 21 centimeter transition to the gas, which is lower than the CMB temperature, and so there's another absorption trough. So this is the history of the signal, the Dark Ages signal and absorption trough. clean from astrophysics, cosmic dawn signal, another absorption trough, which is very model dependent if you want to calculate it theoretically. And then there's the emission signal here from reionization. Experiments targeting this include global signal experiments such as EDGES, that you may remember claimed the detection a few years ago, which was then challenged by the SARS experiment. HERA, an interferometer, which will be able to reach or is able to measure between 6 and 20 something in redshift. So far, only delivered upper bounds, no detection yet, although I think we should be hopeful about the next 2 to 3 years. And then, as I alluded to before, we do have complementary measurements from the same epoch from Hubble and JWST, which measure the brightest objects by definition. So it's a biased measurement, but we can get the UV luminosity function measurements, for example, which complement the 21 centimeter signal. And in the future, with SKA and potentially experiments in space or on the far side of the moon, we'll be able to probe into the dark ages. But this is very difficult, and it's impossible from the Earth due to the ionosphere. Okay, so this was a 21 centimeter signal, but there's additional signal that comes from line emission. And this comes about from emission from atomic and molecular transitions in galaxies. Okay, so this, to show you this, I'll show you here spectra from galaxies. So this is a spectrum of a typical galaxy at redshift 0. And you can see the continuum signal, which is just emission from dust that absorbs light from stars and then, like a black body, shines it back. And on top of this continuum signal, you see these peaks. And these peaks correspond to various atomic and molecular transitions. These are rotational transitions in the CO carbon monoxide molecule. These are fine structure lines in carbon, oxygen, nitrogen. So you can measure, you can target your experiment to measure these emissions from different redshifts and produce maps of the sky. This is a spectrum of a galaxy at higher redshift, and here you can see lines all the way to hydrogen lines, the Balmer lines, the Lyman alpha line, etc. Okay, I should say that if you look at the intensity of these lines as a function of redshift, they very closely match, as you might expect, the star formation history. So it's very clear that in order to calculate what the signal should be, we should model the star formation rate, or vice versa. If you observe these signals, you get a handle on the history of star formation. So what do the maps look like, and what is the advantage? So the advantage is that if you look at the patch of sky, say a degree by a degree on the sky at redshift 5, these are all the galaxies in that patch of sky. This is a redshift bin of like 0.1 in redshift. So a lot of galaxies, but these are not observable. If you place some kind of a realistic threshold on the amount of stars in these galaxies to be able to be, so that they're bright enough that we can detect them, maybe we'll be able to detect with a very expensive campaign, observational campaign, these galaxies. But you can see that with this measurement, you don't really trace the clustering properties of the underlying dark matter fluctuations in this map. However, if you use a cheap instrument like COMAP, for example, and you target at 19 gigahertz, which corresponds to the CO 1 to 0 rotational line transition from this redshift, even with an inexpensive campaign, you can measure this. So what you do here is you pixelize the map and you just count all the photons. You count everything you see, all the photons with this frequency, and you see that this retrieves a lot of the large-scale clustering properties of this map. And you can do it with other lines. You can target the C2 line by observing at 317 gigahertz, and you get a map from the same redshift of a different line. Okay, so this is the promise of line intensity mapping. And with this method, you can really try to probe everything in between what you can observe from galaxy surveys and what you can observe from the CMB, with a lot of interesting epochs happening here. Okay, and this has the advantage of going to larger volumes. The nonlinear scales happen at larger K, and so we have more theoretical control of what's going on, et cetera, et cetera. Okay, so these are the advantages. All right, what is the experimental landscape? Where do we stand now in terms of pursuing these signals? So H1 is ahead of the game, as I said, more than 20 years now since this was first suggested. And this was the situation a few years ago when we did this compilation for the decadal survey by NASA. So these were completed, running, funded, and proposed experiments targeting H1 at the time. These were some experiments targeting CO and C2, and for other lines as well, some other experiments. And if I click, this is the update. So now many more are in green, many that were purple are now in orange, and so the field is advancing. Okay, that's my message. Now let me go through a couple of these to really show you where we stand today. So let's start with Hera. Hera is located in South Africa, and you can see it's already built. You can see it from space. All the dishes are there. This is what a single dish looks like next to some people, 14 meters in diameter. And Hera already has useful upper bounds. Okay, so upper bounds from Hera at least 2 redshift bins have already been used to place constraints on some models of reionization. And in particular on the amount of X-ray heating from the first galaxies. We also have from LOFAR, an experiment in the Netherlands, upper bounds that are beginning to creep into the space where some theoretical models lie. So we don't yet have a detection. We don't even rule out a large portion of the possible theoretical models, but we're starting to get there. So that's what, yes. Yeah. Yes, they are public. Yes, I believe so. Hera we have used, so certainly they are. But LOFAR, I think also yes. Yeah. Yeah, okay. So now let's move to CO map, an experiment targeting the CO line emission. So this is located in the Owens Valley in California. And this is what the experiment looks like. One of these dishes is equipped with an instrument that can measure at 30 gigahertz, which corresponds to CO emission at redshift 3 from the 1 to 0 transitional rotational transitional line. And COMAP already has, in its, I think, season 2 campaign, already has even a tentative detection, okay, of this signal. So this is a signal of CO intensity mapping in the shot noise regime at redshift 3. So it's not yet something you can do cosmology with, but again, we're getting there. We're measuring signal on the sky. This is a tentative detection. It's something like 3 sigma, but we're getting there. The experiment is going to improve a lot, and I'm hopeful that we can have really a mapping of this this signal with time. Sorry, the what? So the way the rest frame is 115 gigahertz. Yeah. Okay, so I should mention SKA. So SKA, again, it's going to be, there are 2 instruments, one in Western Australia. This is it. It's going to look like this. And it has already seen first light this year. So the instrument, some of the dishes are there, they're being deployed, some are there, some have already taken data. This looks like stars, but this is 21, this is radio emission. Okay, so this is actually the first attempts to measure something that is related to 21 centimeter. And in the future, this will be able to map the sky also at low frequencies. That was point sources in radio emission that SKA could see. And this is light from the other SKA campaign, which is in Western Australia, also has seen first light. So these are radio maps of the galaxy. This is already taken data. SKA is only planned to start the official campaign in a few years, but the instrument is there. It's being built. Okay. A very exciting instrument that is now in play is SphereX. So for SphereX, we have to zoom out. We have to go outside of the Earth to space. I prepared this slide before SphereX was launched, and then I used to show this, but now I can show this, which is the actual image from SpaceX that launched the satellite. So you see it's very similar. So anyway, it's on the sky. It's taken data. SphereX, the goal of SphereX is to take a survey, galaxy survey at low redshift, but it has very, very good frequency resolution. And because of the observational strategy, what happens is that the experiment goes like this, goes around like this. And so it measures the poles a lot more than it measures the rest of the sky. Every 6 months, it completes a full view of the sky, but the poles are measured a lot more. So at the poles, they should have enough sensitivity to be able to probe, to do line intensity mapping. So that's the hope. I'll get back to this towards the end of the talk, but that's the idea. Then in the future, in the far future, there are thoughts or proposals for more ambitious campaigns, like a new flagship microwave polarimetry, spectropolarimetry satellite to be launched by ESA. This will be able to map all of these lines at all of these redshifts. So this is really futuristic, but very promising if it happens. It was selected as one of three themes that ESA is examining for its Voyage 2050 outlook. So this means launch either at 2040, 2045, or 2050, but we'll see. And then we even have a mention now at the P5, the Particle Project Prioritization Panel. There's now a recommendation. You see here, LIM. So this is a long list of things that is supported by the Department of Energy in the US, starting with LHC, Xenon, LZ. And if you go, I really skipped like 50 lines here to get to line mapping, but you can see that it's on here. Okay, so it's on the, we're on the path to be funded even by the DOE, and you can see here the different science themes that these experiments are relevant for, and you can see that this is really complementary with the LHC. The only overlap is dark matter, and so far LHC. Well, okay, maybe there's not really overlap there. Okay, so again, this is promising, and the takeaway from this part of the talk is that line intensity mapping is coming, and we should get ready and be excited. What can it probe? So there's a long list of reviews and white papers that have been written about this. In general, it can be used to probe astrophysics or to probe cosmology. And if you try to focus on one, the other is typically a foreground. Okay, because if you want to do cosmology, you really have to worry about the astrophysics. You have to worry about its modeling. If you want to try to study astrophysics, you still have to worry about various things that can come from your cosmology, and be careful about that. I'll mention an example a little later. So first, in the first part of the rest of the talk, I want to focus on cosmology and get back to the teaser that I promised you. So Cosmic Dawn, no longer just forecasts, okay? We can do forecasts of wonderful things we can do when we have this data, but who knows when that will happen. Let's show you some things that are actually based on data that we have measured. So the starting point will be to combine CMB and first 21 centimeter, okay? Line intensity mapping. So for CMB, we have the analogous of the analogy of the global signal, which is the black body spectrum of the CMB. But then we have the anisotropies. Okay, so this is the power spectrum. This is an old measurement, old compilation of Planck, ACT, and SPT, measuring the peaks all the way to the 9th peak. By now, there are updates of this. And then in the 21 centimeter signal, we have the global signal, which is the average signal on the sky as a function of frequency or a function of redshift. And as you can see, there's a large space of possible models depending on the astrophysics. And this is just one particular model highlighted here. But we also have the power spectrum. Okay, so for the power spectrum, we also have various astrophysical models that can lead to different signals, but this is just for one wavelength. Okay, we have data from, if we take data from a lot of wavelengths, we can try to hope to break the degeneracy between the astrophysics and cosmology. So that's the hope, really, is to go for the power spectrum or the fluctuations. I'm less optimistic about the usefulness of the global signal, because look at this. Okay, how do we simulate the signal? There are various methods, starting from full radiative transfer hydrodynamical simulations, which take weeks to run, ray tracing algorithms, one-dimensional radiative transfer codes, which are much faster but very approximated. There are analytic codes, I'll get back to this later, and there are semi-numerical codes using the excursion set formalism. One of them is 21 centimeter fast, perhaps the most widely used. It's a public code written by Andre Messenger and developed since by Stephen Murray and others in Pisa. And this is a starting point for what I'm going to show you next. Okay, so what I'm going to show you next is how to take 21 centimeter fast, which originally was designed to deal with the astrophysics of the signal mostly, and how to turn it into a first-class cosmology code. So the limitations of 21 centimeter fast when thinking about new physics are first that it's initialized at redshift of 35 and does the evolution from there. It starts with homogeneous initial boxes. It assumes that the fluctuations in the baryons in the cold dark matter are the same, which is a good approximation at low redshift, but not a good approximation at high redshift. It does not allow you to probe the degeneracy between astrophysics and cosmology because it does not allow to vary cosmological parameters. And it's very slow in the tight coupling regime. So if you naively extend this to higher redshift, what happens is that you get to a stage where you need to work with very, very, very precise redshift steps in order to deal with cases where the difference between the temperatures becomes very small, but the rate of interaction is very high. Okay, so it requires very small redshifts, which makes the codes very slow. How did we solve this? So we solved this with a code called 21 centimeter first class. It's called first class because it's a great code, but also because it starts with class. Okay, so you run class at redshift to initialize at 1100. And then we calculate recombination history accurately by taking high rec and putting it into the code. We consistently track separately the baryon density fluctuations, the matter density fluctuations, the relative velocity, and the different temperatures. And we, of course, get inhomogeneous initial boxes at 35. We can fold in consistently the cosmic microwave background and, for example, deal with the optical depth. So if you initialize class with some value of tau, and then you run a simulation, you can also calculate tau from the simulation. It will not agree with the tau that you started from. So what we do here is then we run again the CMB calculation again with the tau from the simulation so that the 21 centimeter and the CMB data are consistent. We can explore degeneracies between astrophysics and cosmology easily because we initialize with both sets of parameters. And we also introduce tight coupling approximations to deal with the slowness. And now we have a code that can fully simulate this. It's public, and it does this in only 20% longer than the regular 21 centimeter fast run. So negligible. Okay. You can find it on GitHub. There are detailed Jupyter notebooks that explain how to run the code, how to make plots like this. So I encourage you to do that. And with this code, we can make forecasts, for example, for how we can use 21 centimeter data from Hera and in combination with CMB experiments to probe not only cosmological parameters, but also astrophysical parameters and the degeneracies between them. Okay, but now to go beyond that, and I promised you I'm going to show you analysis of data. We built this, so my student, Chovav Lazar, built this emulator pipeline to analyze 21 centimeter data and other data from cosmic dawn. So what happens here is that we start from a set of parameters, we feed them into class, and also and feed the results into 21 centimeter first class. We get the outputs. We train this with tens of thousands of simulations. This can take maybe a week to do the training. And then we can do inference on data. Okay, so this is the pipeline. It worked well. We've used it to reanalyze the Hera data and reproduce the results from the collaboration. But then to go beyond that, we want to add new observables. Okay, so one example for an observable is the UV luminosity functions from Hubble and JWST. This shows a compilation of data taken from this paper, where the open diamonds correspond to JWST, and the filled circles or diamonds correspond to HST. So you can see we start to have data from redshift 4 all the way to redshift 14. So this is one relevant set of data. And the other data comes from the optical depth from Planck, which does set which is a measurement relevant to cosmic dawn, and the measurements of the neutral fraction. Okay, so we have tau, measurements of the neutral fraction that have been discussed yesterday in one of the talks, and UVLFs. And the point is that 21 centimeter first class can consistently simulate all of these observables together with the 21 centimeter and the CMB, so you can do a combination of all of them when you try to analyze data. Specifically for the UVLFs, what we did is we followed a public code called Galumi, developed by Nashwan Sabti and others a couple of years ago. And what this code does is that first, when it treats the data for UV luminosity functions, it makes several corrections. So this is the raw data from Hubble, the red points here. We compensate for dust attenuation, which brings us back to here. These are the black points. We add some error due to cosmic variance because that's not taken into account in the published data from HST. And of course, we have to, and this gets back to worrying about cosmology. Every time we change the cosmological parameters, we need to. So this is this is a density measurement. sorry, this is a density measurement, of course, and the volume changes when you change the cosmological parameters. So when you calculate, you need to recalculate these points because of the Alcock-Paczynski effect every time you change the set of parameters that you're measuring. Another thing we did is that we updated the pre-existing stellar to halo mass relations typically used in codes like 21 centimeter fast, because you see that it does not agree with the data. So what used to be a simple power law is now expanded to a double power law with redshift dependence, so that it can actually fit the data well. Okay. So now using this, we decided to tackle the fuzzy dark matter model and see if we can say something about it with this combination of data. So first, the 21 centimeter signal, what happens if we have fuzzy dark matter? So if we look at the matter power spectrum and we introduce fuzzy dark matter at some percent of the total dark matter, let's say 10 or 50%, you see the suppression, the typical suppression of small scale fluctuations, which delays the formation of structure and delays the 21 centimeter signal. So if this is the lambda CDM signal, as you suppress the fluctuations more and more, you delay the signal. Okay, so that's, and eventually you erase it almost completely. If you take a very extreme model, which shows you the 21 centimeter data should be very sensitive to this. But there are other observables. We can see what happens to the reionization observables, the optical depth. As you increase as you change the mass, for example, and the fraction of the fuzzy dark matter model, you start disagreeing, you start deviating from the Planck constraint on tau. You also start disagreeing with constraints on the neutral hydrogen fraction. So when you take these into account, as well as what happens to the UV luminosity functions, and this shows you HST data versus what happens when you introduce fuzzy dark matter at higher and higher fractions for a given mass, or you change the mass for a set fraction, say 50%. This is what happens. You slowly suppress structure, and you disagree very quickly with the measurements from Hubble. And this means that if you take the previous constraints on the fuzzy dark matter parameter space, fraction, and as a function of mass, and you see this window here where constraints were weaker, we could fill it up. And there was similar work led by Harrison Winch last year, which shows that when you take the UV luminosity functions, you can close this window. Okay, so this is a zoom in on these constraints, or here. Even with just the reionization parameters, tau and the neutral fraction, you can already sort of at least rule out 100% or 50%. But then with the UV luminosity functions, you get really a tight constraint. I should say that we also have this prediction for the 21 centimeter signal. So the 21 centimeter signal is less, you don't see this diagonal rise that you see with the UV luminosity functions, which comes from the fact that the UV luminosity functions are really sensitive only to the brightest sources. So once you go to higher and higher mass in dark matter and you affect smaller and smaller structure, the UV luminosity functions are less sensitive to that, but 21 centimeter remains sensitive. Yeah. So what we do is we marginalize over all the parameters. We let them float. Yeah, yeah. That's right. Yeah. Everything is marginalized over. Yeah. Yes. Well, it only goes. Yeah. I'm not an expert on dust animation, so I don't know, but it's we can quantify that. Yeah, I don't have anything intelligent to say. But you know, my point is that I don't care if it's here or if it's here. You know, so yeah. Okay. And now we can try to probe other models, for example, dark matter proton scattering. So this shows the suppression in the matter fluctuations. And you have a cross-section of interaction between dark matter and protons that has some velocity dependence. So you can have this velocity independent case, or n equals 2, n equals 4. And this shows you the suppression with the dark acoustic oscillations. And this same suppression will have an effect on the UV luminosity function. So here is, again, the UV luminosity function data. Here I take data from HST plus data from lensing, which goes and probes smaller and smaller scales. And you can see the prediction from the models here. And doing the same type of analysis, we can place a constraint which now rivals the one from Milky Way satellites. So this is a completely different regime. Milky Way satellites is low redshift, very nonlinear, just a handful of satellites. And here we get a constraint from cosmic dawn, from UV luminosity functions, from JWST measuring very bright galaxies at high redshift, and we get very similar constraints. Okay, so this is nice. So what else we can do? And this is to summarize the first part of or second part of my talk. We need robust, consistent, and fast simulations if we want to do this type of analysis. Line intensity mapping, in particular, is unique in many cases because it can probe things that these other observables cannot probe. And at small scales, we can constrain fuzzy dark matter, interacting dark matter, and we can go on and these people have written papers on primordial magnetic fields, early dark energy, self-interacting neutrinos, neutrino masses, et cetera, et cetera. We can do all of this, okay? So I welcome you to look at papers on the archive recently. Okay, now let me focus on the other side, the astrophysics side, where I promised a teaser, which is whether we can time the onset of reionization. So going back to this picture, what this shows you is that we are targeting all of these lines at the same time. Okay, and in particular, this approach of measuring different line emissions is very useful at reionization. And why is that the case? Because if we look at a typical illustration of what happens at reionization, these lines provide complementary information. Lines like CO and C2, which are very intimately related to star formation, give you a probe of what happens in the galaxies, in the point sources. Lyman alpha is an extended diffuse signal, which probes into the ionizing bubbles. 21 centimeter comes from outside the ionizing bubbles. So by measuring all of these lines together, we can really get a full picture of what's going on. And this is an idea that dates back to about 15 years ago, first promoted by Adam Lids and others. And here's a nice plot that Adam made, where he shows a set of galaxies at the EOR. The predicted signal from the CO 2-to-1 transition with line intensity mapping. So you see the typical low resolution map of all the photons corresponding to this transition from this redshift. This is the ionization field, and this is the redshifted 21 centimeter signal. So you can see the clear anti-correlation once reionization is in motion, in full motion. This is at about something like 40% or 50% of reionization. You can see the clear anti-correlation between CO and 21 centimeter. The best thing about this is I think this will be the best way we have to verify a measurement of 21 centimeter or of the other lines at reionization. It's going to be very hard to convince ourselves that we actually measured either of these signals, but if we see the anti-correlation, that's a very good thing. But then I want to go beyond that and probe the onset of reionization. So what is the starting point? We need to combine now 21 centimeter and other lines. And here we took a different approach, and we followed this code written by Julian Munoz a couple of years ago called Zeus 21. So what does Zeus 21 do? It's an analytic code to calculate the 21 centimeter signal. What it does is that it uses this approximation or this assumption that the star formation rate density traces the underlying density field as an exponential, okay? Because it's only at the very extreme parts of the density field where halos form, galaxies form, and we have star formation rate. So the star formation rate is really a log normal of the density field. And you can calculate the star formation rate smoothed over different radii as log normals of, sorry, I was pressing this. Yeah. As log normals of the density field smoothed over different radii. And you have a set of these exponential bias parameters, which are effectively what allows you to do this calculation. And once you have this, you can calculate the Lyman alpha flux, the X-ray heating flux, and various things that you need to calculate the 21 centimeter signal. And also there's the advantage that the correlation function of a log normal SFRD can be computed analytically. So you can analytically calculate the 2-point function just based on this assumption with no simulation. So this takes seconds. So what we did here, or more correctly, what Sarah did, is she extended the Zeus code into a code called Olympus, which does a similar thing, but for line luminosity. So instead of measuring the star formation rate density, what she does is calculate the luminosity density based on the same assumption of the log normal approximation, but here taken to second order. because for line intensity mapping, we really need the small scale information to be correct. And we found that we need to extend this to second order, but it's still fast, it still works, and allows us to produce light cones of density field, 21 centimeter, and these other lines in seconds. Okay, so this shows an animation, and here we show, I showed the ionization field, the 21 centimeter signal, and these other lines. Okay, so the 21 centimeter starts negative at the beginning, at somewhere during cosmic dawn. Then the gas gets heated, so it becomes positive. That's where star formation rate is enough for these other lines to become prominent. And then reionization proceeds and ends up killing the 21 centimeter signal. So no reionization yet. Now reionization starts. We see the 21 centimeter signal slowly getting killed, and that's it. And now I get back to the question of how to detect the beginning of reionization. Okay, and so here what I show is the progression of the reionization epoch and the global signal of the 21 centimeter emission. So you see, and I mark here in gray the range of where the ionized fraction is between 1 and 10%. So this is the gray area is the beginning of reionization. So you can see what happens to the global signal of the 21 centimeter. It starts tapering off, peaking, and then falling because reionization is progressing. But the question is whether there is anything special about the 21 centimeter signal here that can be used to detect where reionization is happening. The issue is that it's true that some areas are getting ionized, and so the signal goes to 0 in the 21 centimeter case, but parts of the IGM are still heating. So these are compensating effects. And we don't know exactly when reionization happens. This is very model dependent in the 21 centimeter case. So the question is whether there's something that we can do that will be very sensitive to reionization specifically, okay? And to get an idea for what to do, let's focus on the high density peaks. So if we focus on the high density peaks in this 21 centimeter map, we see that stars form faster in the high density peaks. The IGM heats faster in the high density peaks. It also ionizes faster in the high density peaks, but other lines are also emitted faster in the high density peaks. So this leads us to the idea to cross-correlate, okay? Maybe we can cross-correlate the signal from 21 centimeter with the signal from the other line. Let's see what that cross-correlation, just a simple one-point cross-correlation, you just multiply the different pixels, okay, and normalize between the two maps. So what will the Pearson coefficient, this cross-correlation coefficient, look like between 21 centimeter and another line? It will start out negative because at this redshift during the cosmic dawn trough, because the 21 centimeter signal is in absorption and it's negative. Okay, so it will start in that, while the line intensity mapping signal is always positive, so it will start out negative. At some point, gas heating will turn the 21 centimeter signal into a positive signal, and then the cross correlation will become positive. Now, what's very important here is that typically, in almost all the cases, if you look at the astrophysical modeling, the IGM heating is very efficient before ionization starts, which means that this cross-correlation will saturate. It will reach a peak where the 21 centimeter and the line are perfectly correlated before reionization starts, okay? So what happens is we get the peak, and then once reionization starts, this 21 centimeter signal starts getting killed, and so the peak, we start dropping from this peak, okay, in the cross correlation, until we at some point cross 0 and it becomes negative again, like the picture I showed you a couple of minutes ago, and from the illustration by Adam, where the anti-correlation happens because the regions that were ionized are exactly the regions where the intensity mapping signal is highest, but the 21 centimeter signal is low. So it goes negative again until it goes to 0 because the 21 centimeter signal is killed at the end of reionization. Okay, so this is the shape. And now this is where 1 to 10% of reionization is. And you can see here this drop is only due to reionization. Okay, so if you can detect this drop, you can detect when reionization starts. That's the idea. All right, so now let's add this panel, the Pearson coefficient panel, to the simulation, and you can see the peak and the drop at around 10% of reionization. Now, is this robust? So this is, I should say that we just wrote a paper about this, and you can look at it, but we can ask ourselves, is this robust? So first of all, I tried to ask Grok, if I consider the cross correlation between 21 centimeter temperature and the O3 intensity mapping signal, what should it look like? And immediately it explained this, and then it asked me if, so this is exactly, this is in words saying that it will go up, then there will be a peak, and then it will drop. And then it asked me if I wanted the Python code to simulate the signal. I said, sure. So it sent me this, and I just copied and pasted into Python, and I got this. Okay, so it's exactly, looks exactly what like the signal we calculated from Olympus. So this was very nice. Then I asked Grok, so do you think this is a good measurement of the onset of ionization? And of course, everything you ask ChatGPT or Grok, they always say, yes, it is. And so yes, it is. So I thought, okay, so if it knows about this, maybe I can use something like Denario. So we got in touch with Paco, and we ran Denario on sets of simulations from Olympus, and we got very crappy papers claiming a robust detection of the onset of ionization, but these are all crap. So I should say this is in progress, but maybe I think this is crap because our prompts and the data that we gave Denario were not good enough, and it tried to do all kinds of machine learning type stuff which were not relevant. But this is in progress. But here I show results using 21 centimeter fast, the newest version of it, version 4, and you can see again something very similar. So here the astrophysical modeling is very different. A lot of details in the simulation are different. Reionization happens for this case much earlier, but you can see still here the same exact shape of the Pearson coefficient, and again the drop happens at around 10%. And we've tested this for a wide range of parameters. Parameter values, and if you want, I'll show you more results during the question session. Is this detectable? So getting back to SphereX, I told you that by observing the poles, we can hope to do some line intensity mapping. So this will be the redshift coverage of SphereX for different line emissions. And you can see that there's some hope to get to these redshifts 8 to 12, more or less, where we, for at least some models, expect this drop, where we can try to do this cross-correlation if we have another 21 centimeter measurement to cross-correlate with. And there's actually a campaign now by COMAP. This is the same experiment that targets CO at low redshift. They also measure a higher rotational transition at high redshift. And they now have funding for a COMAP-wide experiment, which will cover a large footprint on the sky that overlaps far. And they're going to try to do this precise measurement. Okay, so maybe there's hope to do it. So to summarize this, again, we need robust, consistent, and fast simulations. Line intensity mapping is unique, and we can probe various things. So I showed you that we can maybe probe the onset of ionization with the first estimator that can do this. We can, of course, probe the bubble morphology, the full star formation history, things like population 3 galaxy abundance by looking at line ratios, feedback-free starbursts. An idea to explain the measurements by JWST can be probed by 21 centimeter intensity mapping, and anything really to do with gastrophysics can be done with measuring lines. Okay, and I'll stop here. Sorry, yes. The constraints for dwarf galaxies covers some of the range. Yes, there is, yeah. But they're weaker than the ones I showed. Yes. Nothing. There. So the assumption there is that you go straight from the density to the star formation rate. It's so Julian shows that it's a very good approximation. You can see in his paper comparisons between 21 centimeter fast and his code, they agreed to like 5%, 3%. It's in the calibration. You have to calibrate the bias parameter, this exponential bias parameter, but it's a very good approximation. And this is because it's really because the dependence on the density is exponential. It's really in the very high density peaks that that star formation is happening. So we do this for every scale. It's like it's the same excursion set formalism that is done. That's right. So again, this is it's an approximation, but and you have to do this for various smoothing scales, and there's a different bias parameter or this exponential coefficient for every smoothing scale, but it works very well. What do you mean one? Oh, certainly these bias parameters are correlated. They're not independent of one another. Yes, that's true. But if you want to, the thing is that the 21 centimeter signal is not local, right? Because it has to do with the emission. There's the escape fraction and the X-ray heating, and this is not. It's an inherently non-local signal, and so you need in the excursion set formalism. What you do is you smooth over different radii, and that's how you calculate the flux. And so you need an approach like this. The idea is to mimic what is done in codes that do the excursion set formalism, like 21 centimeter fast, but in an analytic way. That's the idea, but it's the same. It's still the same excursion set idea. Yeah.
Very complex transforming regions. We thought that the revision was driven by different galaxies and now effect agent. How easy is it to put this thing up? What was it higher or was it with all of these effects just one scale, but they propagate out there? But black holes not. The X-rays, black holes can be really
Yeah, so there are, I point you to papers by other people from the past year or so, like detailing exactly how to do that. But I haven't worked on this. So. Yes, yes. Whether you believe the models or not, yeah. But yes, people are working on this. Mm-hmm. Mm-hmm. But the other codes now they are a bit different. As far as I have, not an yeah, we can discuss maybe later. Very simple one. Yes. Mm-hmm. Mm-hmm. That's right. Mm-hmm. So this is the reason we had to go to second order, because really the signal is coming from the highest density peaks. But we showed that it's a very good approximation. So this is detailed in the paper, and we can discuss more if you want. But this is exactly the reason we had to go to second order for the lines.